Hi everyone, I'm Hui Song, a PhD student at the University of Iowa. Today I'm going to introduce our work, Rethinking Graph Data Placement for Graph Neural Network Training on Multiple GPUs. Graph neural networks, also known as GNNs, now is the state-of-the-art models for machine learning tasks on graphs. They make predictions with node features, but on large graphs, node features data could exceed the memory capacity of GPUs. So it's challenging to train GNNs efficiently on large graphs. To support large graphs, a straightforward approach is to partition the graph and distribute the node features onto multiple GPUs. In this figure, we show the breakdown epoch time of GNN training with two graph partitioning methods, PPoPP' and dist.dgl. It shows that the loading the input features is still a performance bottleneck. dist.dgl and PPoPP' were both proposed recently. DGL adopts Mantis graph partitioning. It assumes that the graph can be entirely stored on multiple GPUs. Thus, it can not work for large graphs that exceed the memory capacity. PPoPP' uses a heuristic partitioning method based on training nodes, and for large graphs that exceed the memory capacity of multiple GPUs, it stores the graph on CPU and buffers the most frequently accessed nodes of each partition on GPU. To reduce the data loading overhead, we first proposed a performance model of data movement among CPU and GPU in GNN training. For a specific GPU, we assume that the cost of reading a node on the same GPU is zero. The cost of reading a node on a different GPU is tGPU. And the cost of reading from CPU is tCPU. If tCPU is smaller than tGPU, every time we need to fetch all nodes from CPU. On the contrary, we need to read as many nodes as possible from GPUs first and read the rest of the nodes from CPU. Our goal is to minimize the maximum cost across all GPUs. To achieve this goal, we propose an efficient solution. Here's the sorted nodes by probability in descending order. When tCPU is smaller than tGPU, we store nodes with the highest sampling probability on each GPU. When tCPU is larger than tGPU, we initialize the buffer on each GPU with the nodes of highest sampling probabilities. Then we need to replace the node on each GPU from the last nodes with the following nodes here. For example, in the first replacement, we would like to replace node 4 on GPU 0 with node 5. If the replacement is beneficial, we perform the replacement. Follow the same steps. We replace the node 4 on GPU 1 with node 6, and we replace node 4 on GPU 2 with node 7. And notice that we will not change node 4 on GPU 3 here, because it has high sampling probability, and intuitively we should store at least one copy of it. You may have a question on which GPU we will use for the next replacement, right? To ensure each GPU has a similar data movement cost, we maintain the sum of sample probability of the new nodes, and every time we select the GPU with the lowest sum of sampling probabilities of new nodes in each round of replacement. Okay. We evaluate our technique with two interconnect configurations. The first one is every two GPUs are connected. The second one is all GPUs are connected. We can see that our data placement strategy achieves smaller data loading time than both PPoPP' and DGL, and our technique is more effective on for GPU. And because of two GPU buffers are used together, the improvement of 2++ is not as good as 4 GPU. Thanks for your listening.